Hello dear students, I hope you are all doing well. I'm back again with another video lesson. In a previous lesson, section 3 in chapter 6, we studied the effective current in AC circuit. You know that we have two types of circuit, AC circuit and DC circuit. In AC circuit, we have three different values like the effective values, the maximum values and the instantaneous values. But in DC, we have only one value, which is the maximum value for potential difference and the current. And also we studied that if two circuit, like we have two maximum current in AC circuit and DC circuit, okay, like maximum current 10 ampere in DC and maximum current 10 ampere in AC, which one has more power dissipation? Absolutely the DC. The maximum current 10 ampere maximum current in DC has more power dissipation because current in DC source is continuously without changing. Okay, it is magnitude, it's continuously 10 ampere. That is why it has more power dissipation. But in AC circuit, the maximum 10 ampere in AC circuit has maximum value only at one instant. Okay, so it is not continuously 10 ampere, only at one instant. The maximum current in AC circuit is equal to 10 ampere. So that is why power dissipation is more in DC circuit at constant resistor than power dissipation in AC. So power dissipation in DC circuit is twice as much of power in AC circuit in a given maximum current. Guys, today's lesson we are focusing on the applying Ohm's law to AC circuit. Applying Ohm's law to AC circuit. We have three different cases. The first case, pure resistance circuit. In pure resistance, what do you mean by pure resistance? Pure resistance, a resistor with no cell of inductance. A wire without like coil, okay, without cell of inductance. We have only wire. Connecting to AC circuit. Look, pure resistance. Pure resistance. To AC circuit. We have to connect an AC circuit. This is AC source with a resistor. This is resistor. This resistance is pure resistance, okay? And we have a meter for measuring current, and we have voltmeter for measuring potential difference across the resistor. In pure resistance to AC circuit, pure resistance in AC circuit, it means that we have only resistance. We have what? Only resistance. Okay? In AC circuit, in this case, the current across the resistance and the potential across the resistance, they are in phase, and there will be no leading and lag between the potential difference and the current. Okay? Both resistance and potential difference are, both current and potential difference are in phase. Okay, once again, listen carefully. In pure resistance, in AC circuit, potential difference and current are in phase. There will be no leading and lag between the potential difference and the current across the resistor. Okay? What do you mean by this? It means that when we close the switch and when we switch on the circuit, both ammeter and voltmeter reading the current and the potential difference, both of them increase and decrease together. Both of them decreases, both of them increases. Both of them reaches maximum, both of them reaches maximum, okay? Like, this is, assume that this is current across resistor and potential difference across resistor, okay? Both of them are in phase, and the phase difference between current and potential difference is zero. The phase difference is equal to what? Phase difference is equal to 0. So angle between I and potential difference is equal to 0. And so obey Ohm's law, we can find resistor in pure resistor at each instant. Like in the Ohm's law, according to Ohm's law, how can we determine the resistor across the resistance? Resistor is equal to VE total over IE total. Resistance is equal to VE across resistor, IE across resistor, and is equal to also VM across resistor divided by IM across the resistor. So we can find resistance at each instant for the resistor. R is equal to VR over IR, VM over IA, V over IE. Okay? So the phasor diagram will be like this because both current and potential difference are in phase. Both potential difference and current are in phase. So the phasor diagram will be like this. Current, potential difference across the in a circuit are in phase. Assume that the yellow represent for the current. Assume that this is current. Okay. And the green one is for potential difference. Guys, look. This is potential difference. When current is zero, potential difference also zero? Yes. What do I mean by this? It means that phase difference between current and potential difference in pure resistance to AC circuit is zero. Phase difference in pure resistance to AC circuit is equal to what? Is equal to zero. Why? Because when current is zero, read is zero, potential difference also zero. When current reaches maximum, potential difference also reaches maximum? Yes. When current again reaches zero, potential difference also zero? Yes. Phase difference between them is what? Is equal to zero. In pure resistance circuit, potential difference and current in phase. What do we mean by in phase? It means that same phase difference. Okay, or phase difference is zero. Okay, write down phase difference is zero. Is zero, which means the phase difference between potential difference and the current is zero. When pure resistor is connected across source of the frequency 0.1 hertz, we can choose a central zero for voltmeter and ammeter. What? Voltmeter and ammeter. Know that the reading of voltmeter and the ammeter increase or decrease together. What do you mean by increase, decrease together of voltmeter and ammeter? It means that both current and potential difference are in phase. Potential difference with the same phase difference, okay? Resistance of the ohmic resistor independent on the frequency. Resistance, guys, in pure resistance to AC circuits does not depending on frequency. Why? Because this resistance can work with both types of the source, AC source and DC source. Resistance can work with DC and AC, okay? Does not depending on the frequency. In DC source, we don't have frequency. Frequency is zero, but resistance can work with the DC source also, okay? So that is why the resistor and the resistance does not depend on the frequency. Independent of the frequency of the source. It's follow Ohm's law, which means that pure resistance can be found anytime, Vm over Ia, Vr over Ir, V over Ie. It follows Joule's law, which converts electrical energy into thermal energy. Guys, in pure resistance to AC circuit, when the current passes through the resistor, electrical energy, this is electrical energy, okay? This electrical energy converted to what? Thermal energy. Or light energy. And light energy, or you can say and light energy. Okay? In a pure resistance to AC circuit, the electrical energy is converted into what? Thermal energy and light energy, like a light bulb. Light bulb is a resistance, okay? The light bulb convert electrical energy into the thermal energy and light energy. So it means that it follows the Joule's law. Energy dissipated in the resistance, guys, be careful. Energy will dissipate in the resistance, okay? When the current passes through the resistance. Convert electrical energy into the thermal energy. The equation of instantaneous current and instantaneous potential difference will be like this. Guys, the equation of instantaneous potential difference across the pure resistance is equal to what? Vm sine omega t. Current, instantaneous current across the resistor is equal to what? Im sine omega t. We don't have lead and lag between potential difference and current. Phase difference between them is 0. There will be no leading and no lagging between the potential difference and the current. Power dissipation is equal to energy per unit of time. Energy is equal to what? Power of time. Or power times time, sorry. Guys, look. Power is equal to what? The time rate of the energy. Energy per unit of time. E is equal to what? Power times delta T. What is this? This is loses energy or lost energy. To find E lost, power P lost is equal to what? I squared R times delta T. E lost, you can use VE squared over R times delta T. Okay? Why? Because power is equal to what? Is equal to IV. We studied. And power is equal to what? VE squared over R. Power is equal to IE squared R. Is it clear? Okay. Energy is equal to power times delta T. Power times delta T. Power times delta T. This is power, and this is power. Only we analyze it here. Look at sample problem 6D about the pure resistance to AC circuit. The sample problem says an electric heater operates under a potential difference Vm. What is this? Maximum potential difference. Vm. Vm 282.8 volt. If the resistance, so it means that this question is about the pure resistance in AC circuit, of the heater is 500 ohm. This device that's connected with this source, it has a resistance 500 ohm. Calculate the generated heat energy. What is unknown? Generated heat energy and the energy dissipated in the resistor. If the current runs in the heater half an hour, time half an hour is equal to 1 over 2 hour or 0.5 hour, which is equal to 30 minutes and 1,800 seconds. Time should be in seconds. Half an hour, 0.5 hour, 30 minutes, 1,800 seconds. Okay? Use radical 2 is equal to 1.404. What is, guys, what is the effective value of the current? What is unknown? The effective value also. How many unknowns do we have? 2. Generated heat and the generated heat energy and effective current. Guys, look. How can we at first determine E, generated heat energy? E is equal to what? IE square R times T or VE square over RT. VE square over RT. Why? Because we don't have IE. VE square over R times delta T. This equation can be used to determine E. VE square over R times delta T. Guys, look. Do we have VE? No. VE is equal to what? VE is equal to Vm divided by radical. 200. Do we have Vm? Yes. 282.8 divided by radical. VE is equal to what? VE is equal to 200 volts. 200 volts. Okay? So, now, how about replace into this equation? Sorry. Replace into this equation. Energy generated heat is equal to VE square is equal to 200 square. Divide by resistance 500 times time 1,800. Okay, energy generated as heat is equal to 144,000 joule. Okay, this is the generated heat energy in this resistance. In the second unknown, IE is equal to what, guys? IE is equal to, can we say IM over radical 2? No. Why? We don't have IM. Do we have IM? No. We cannot use this equation to find IE. And instead, you have to use Ohm's law. In Ohm's law, VE is not equal to IER? Yes. IE is equal to what? VE over R. Do we have VE? No, we didn't have, but we found. This is VE. 200 divided by resistance was given 500. I effective is equal to what? 0.4 ampere. So this is sample problem 6D about pure resistance to AC circuit. Practice 6D. A resistor of resistance, which means R. Question 1 in practice 6D. R is equal to what? 20 ohm. Connected across an AC source. AC source resistance. Connected resistance. Connected to what? AC source. Okay? With 20 ohm. Effective value 10 volt. Effective value 10 ohm. 10 volt, sorry. Effective value, RMS value, 10 volt. Calculate maximum and effective value of the current. Maximum and effective value of current. IM, VM. Okay? IM, VM. How can you determine IM, IE? Sorry, IM, IE, not IM here. To find IE, VE is not equal to IE times R? Yes. IE is equal to what? Ohm's law. VE over R. Do we have VE? Yes. 10 divided by 20 is equal to 0.5 ampere. What is this? This is IE. This is IE. If we have IE, how can we determine IM? IM is equal to IE radical 2. IM 0.5 radical 2 ampere. 0.5 radical ampere, which is equal to 0.707 ampere. Okay, so this is question 1 in practice 6D. Question 2. Question 2. Guys, look at question 2. If the frequency of the source in item 1 related with item 1, 50 hertz, frequency 50 hertz, write down the expression of the instantaneous current and potential difference. Write down what? Expression of the instantaneous current and potential difference. To determine and to write the expression of instantaneous current and instantaneous potential difference, so you have to write down these two equations. Guys, look. V instant, Vm sine omega t. For I instant, this is the expression of the instantaneous current and potential difference in pure resistance. Im sine omega t. What we need? We need Vm, omega, and Im. Okay? So we need what? Vm. Vm is equal to what? I don't know. We have to calculate. Okay? How can we determine Vm? So in the previous equation, we had Ve. Okay? In the previous question, we had what? Ve. Ve is equal to what? 10. Vm is equal to what? Ve times radical 2. Ve was given in question 1, 10 radical volt. We found Vm. Put into this equation. V instant. Instead Vm, write down what? 10 radical 2. Sine. Instead of omega, omega is equal to what? Omega is equal to 2 pi f. We have frequency. 2 times 50, 100. 100 pi rad per second. Sine 100 pi time, sorry. So this is the expression of instantaneous potential difference. That's all. This is the final answer for the potential, instantaneous potential difference across the resistor. Okay? Look, the final result is what? 10 radical 2 sine 100 pi t. Now, the expression for the current. We need what? Im. We need to find Im. Do we have Im? Look at question 1. Im we didn't have, but we found in the previous question, question 1. Yeah, Im, we have Im in item 1 is equal to 0.707 ampere. Omega is the same, 100 pi. Replace into this equation. I instead of Im, 0.707 sine, instead of omega, 100 pi, and t. Don't forget this t, please. This is the final answer for the expression instantaneous current across the resistor. I is equal to 0.707 sine 100 pi t. Last question, calculate the energy dissipated in the resistor in item 1 during 5 minutes. What is unknown? Energy dissipate, which is equal to what? I square R times T. In item 1, do we have IE? Question 1? Yeah, 0.5 squared. Resistance? Yeah, we have to use the same resistance in question 1, 20. Time, in how many minutes? 5 minutes. 5 minutes is equal to what? Time is 60, 300 seconds. 300. Energy dissipated in this resistor is equal to 1500 joules or 1.5 kilojoule. Okay, that's all about the pure resistor to AC circuit. So we have another case, a pure cell of induction circuit. Pure cell of induction circuit. And instead of resistance, we have a pure induction. Okay, pure cell of induction, a pure coil. Guys, we have two different types of coil. Pure coil, which is called pure cell of induction, and not pure coil. So the coil in not pure in a pure coil, guys, look, pure coil in AC source, we have only XL. We don't have resistance. We don't have resistance, okay? When we say pure coil, what do we mean by pure coil? The coil has no resistance. Guys, this is imaginary. This is ideal. But in reality, we don't have coil without resistance. Every coil has its own resistance. Why? Because when the current passes through the coil, there is a resistance between the charge and the particle of the wire. So that is why there will be a friction between the charge and the atoms of the wire, the particles of the wire. So that is why it has resistance. But when we say pure coil, you have to assume that, imagine that this coil has no resistance. But actually, in reality, has resistance. But you have to treat with this coil has no resistance. When does R is equal to 0 for the coil? When the question says pure induction, pure coil. But not pure coil. What do you mean by not pure coil? It means that the coil has resistance. We have both resistance and inductive impedance. In this case, when the question says a coil of resistance, it means that this coil has no pure coil. It is not pure coil, it has resistance. We have to count for both the resistance of the coil and the impedance. Okay? What do you mean by pure cell of induction? Is a coil given cell of inductance but of negligible resistance. Negligible what? Resistance. Okay? So the circuit in pure cell of induction consists of what? AC source, ammeter, voltmeter, connected with what? This is pure cell of induction. What is this? Pure cell of induction. It has coefficient of cell of induction and XL. But we don't have resistance. Why? Because we have pure inductance. Pure inductance. In pure inductance, resistance is equal to what? 0. Okay? Guys, when this is IE total, VE total, when the current passes through the circuit. When the current passes through the circuit. Guys, what happened to the current when passes through the coil? According to Oersted, when the current passes through the coil, this current produces the magnetic field. So in this case, all the current converted into what? Into the magnetic field. So why? Because the coil produces inductive impedance. Okay? The inductive impedance, the impedance what? The flow of the current. When all the current is, the potential difference reaches maximum, but current is zero. Current reaches zero here. Why? Because all the current converted into what? The magnetic field. Okay? When the current passes through the coil, the magnetic field produces in this coil. Okay? So the reading of voltmeter reaches maximum while the current is zero. Okay? After that, all the magnetic field converted into the current, induces the current. Why? Because the inductance can induce the current when the magnetic field changes. Okay? As the current decreases, the magnetic flux changes, and all the magnetic field converted into the induced current. So when the current reaches maximum, potential difference becomes zero. Okay? So it means that in pure inductance, potential difference leads current by phase pi over 2 or 90 degrees. In pure inductance, potential difference leads current by pi over 2 or 90 degrees. What do you mean by this? It means that the phasor diagram between the potential difference and the current. So this is current across the inductance, and here is VL. According to this figure, potential difference leads current by what? Pi over 2. Potential difference leads what? Current by phase pi over 2. Okay? So can we say current lags behind potential difference? The same thing. Okay? But when you say potential difference leads current, okay, by phase pi over 2 or 90, the expression of instantaneous potential difference and instantaneous current will be like this. V instant across inductance is equal to Vm sine omega t plus pi over 2. Why? Because the phase difference between V and I is pi over 2. Phase difference is pi over 2. You have to add pi over 2. But for the current, don't write this difference, because so you have to write only one times for this difference. Okay, it becomes Im sine omega t. Okay? When we say potential difference leads current, the expression of instantaneous potential difference is equal to Vm sine omega t plus pi over 2. Plus what? Pi over 2. Why? Why plus? Because leads. But the current is like this. Im sine omega t. And don't write minus pi over 2. Okay? Because if you subtract with pi over 2, the phase difference becomes 0. And so the phasor diagram between the potential difference and the current is like this. The yellow, like for the current, okay, current 0, Mach is 0, Mach is 0, okay, like this. And the green one is like, the white is the potential. What? This is potential difference, okay? Guys, when current is 0, potential difference maximum. When potential, this is V, and this is I. The yellow curve is I, and the white curve is potential difference. Guys, look. At this point, potential difference has maximum value, but current 0. When potential difference reaches 0, current becomes what? Maximum. And so on. When potential difference reaches maximum, current becomes what? 0. Okay? What do you mean by this? It means that in pure cell of induction, potential difference leads current by pi over 2. When the circuit switch on, the voltmeter reading is what? Maximum. Voltmeter reading what? Maximum. While current, 0. Which means that the intensity EMF coil becomes maximum. But ammeter read is what? 0. Which means that the current is 0. But when the voltmeter read is 0, current becomes what? The reading of the ammeter maximum. Okay? So in this way, you can comparing between the potential difference and the current, and you have to say potential difference lead this current by pi over 2. In the cell of inductance, instead of resistance, in pure resistance we had resistance R, but in inductance, instead of resistance we have impedance. They have the same like function, but in different ways. Okay, inductive impedance XL. What is XL? Inductive impedance. XL is what? Inductive impedance. Measured in what? Ohm. XL is equal to what? Vm over Im. Or VE over IE. V across inductance, I across inductance. It obey Ohm's law? Yes. Yeah, Ohm's law. It obey Ohm's law. It means that we can find inductive impedance by these three equations according to Ohm's law. Okay? If effective value of potential difference and effective value of the current is given, can you find inductive impedance? Yes. We have another two equations to determine XL. XL is equal to what, guys? Omega L. Angular speed times the coefficient of cell of induction. Coefficient of cell of induction. What is this? Angular speed. What is this? Coefficient of cell of induction. And omega is equal to what? 2 pi FL. Replace into this equation. XL is equal to what? 2 pi FL. If frequency and coefficient of cell of inductions are given in the question, can you find inductive impedance? Yes, is equal to 2 pi FL. What does coefficient of cell of impedance depend on? It depends on frequency and coefficient of cell of induction. Or you can say it depends on the angular speed and the coefficient of cell of induction. And with both of them is directly proportional. What is the relation between XL and F? Directly proportional. XL and coefficient of cell of induction, directly proportional. Okay? What does inductive impedance depend on? Frequency, direct, coefficient of cell of induction, directly proportional. Guys, XL is equal to 2 pi FL. XL measured in what? Ohm. Frequency, hertz. L, Henry. Or you can say Henry over second. Henry is equal to what? Ohm second. This is very, very important. Be careful. Okay? Yeah, when L is given with the frequency, you can find XL. Guys, it follows Ohm's law. You can find XL at each instant, but it doesn't obey Joule's law. Why? Guys, in pure inductance, we don't have resistance. Resistance is equal to what? 0. When resistance is equal to 0, P lost is equal to what? 0. We don't have power dissipation in pure cell of inductance. Why? Because resistance is 0 in pure cell of inductance. When resistance is 0, power dissipation 0. Energy dissipation in the coil is 0. The current does not convert into the thermal and heat. The electrical energy converted into the magnetic field. Okay, and after that, the magnetic field in turn induces the current again. Okay. It does not obey Joule's law because power does not dissipate. In DC circuit, XL is 0. Guys, be careful. In DC circuit, if the coil is not pure, okay, it means that R is not equal to. The coil has only resistance, but XL 0. Why XL 0? The source is what? DC. In DC source, do we have frequency? No. In DC source, frequency equal to what? 0. XL is not equal to 2 pi FL. When frequency is 0, XL also is what? 0. In DC circuit, inductance, coil with DC circuit, if the coil is not pure, we don't have resistance. We don't have inductive impedance XL. Only we have resistance. Okay? Because frequency is 0. Guys, look at this note. Coil behaves in 3 different ways in electrical circuit. What is the source? DC. If we connect a direct current DC source to a coil and the coil is not pure, okay, then there will be only resistance, not inductance. This coil is not pure. If the coil is not pure, we have only resistance, but we don't have XL. Why? Because frequency in DC is 0. XL 0 and resistance of the coil is equal to what? VDC over IDC. But if we have AC and the coil is pure, this is pure coil. In pure inductance, do we have resistance? No, we don't have resistance. Only we have XL. Why we have XL? Because we have AC source. In AC source, we have frequency. How about if the coil is connected with AC and the coil is not pure? Not pure. We have both XL and R. When does in the coil we have both resistance and inductive impedance? If the coil is connected with the AC source and the coil is not pure. The coil is not pure coil. Okay? How can we determine for the not pure coil? Not pure coil. What do you mean by not pure coil? It means that the coil has resistance. If the coil is connected with AC, this is AC source. Okay? And okay? And also we have a resistance. We have the resistance. Okay? If the coil is not pure, it means that we have both R and XL. How can you determine potential difference across the coil? If the coil has both inductive impedance and resistance, it means that the coil is not pure coil. How can you determine potential difference across the entire coil? The coil, which has both resistance and inductance, you have to use this relation. V coil is equal to what? Is equal to VR of the coil square, VL of the coil square. Okay? Why? Because we have both resistance and inductance. Is it clear? In this way you can find V coil. Why the Pythagorean theorem can be used? Why? Because between resistance, guys, look. This is VR and this is VL. If you remember, VR with IR in phase, but VL with IL 90. Angle between VL and VR is 90 degrees. The total, which means V coil, we have to use Pythagorean theorem. Pythagorean theorem. Look at sample problem 6e. A coil of pure self, L, coefficient of cell of inductance. L is given is equal to what? L? 0.2 Henry. Okay? Negligible resistance. What do you mean by negligible resistance? R is equal to 0. It means that this coil, pure coil, has no resistance. Connected across an AC source. Frequency is 50 hertz. Okay? Find the cell of impedance of the coil and the effective current through the effective potential of what is unknown? Cell of impedance of the coil. Cell of impedance of the coil, XL. And effective current, IE. If the effective potential difference, VE, 125.6 volts. And write down the expression of what? Current and potential. The equation. I instant, V instant. I instant is equal to Im sine omega t. V instant is equal to Vm sine omega t plus pi over 2. Now, We have to find XL. XL is equal to what? Because we have frequency and coefficient of self-inductance, 2 pi f. Just replace. Which is equal to 62.8. Oh, it's very easy. Because we have L and F, you can easily find XL, which is equal to 2 pi times frequency times coefficient of self-inductance. Guys, how about IE? We cannot use IE is equal to IM over radical because we don't have IM. You have to think about the Ohm's law. IE is equal to VE over XL because XL is equal to VE over IE. How did we get this equation? Look. XL obey Ohm's law. VE over what? IE. How about IE? VE over XL. Do we have VE? Yes. Effective value 125.6 divided by what? XL. We didn't have, but we found. I effective is equal to what? 2 ampere. Okay? So the expression of instantaneous current and potential difference across the inductance is equal to what? So we have to find IM, which is equal to IE radical to VM, VE radical to omega 2 pi f. F 50, 100 pi rad per second. This is omega. I in instantaneous is equal to Im sine omega t. Do we have Im? Yes. IE radical to 2 radical to sine 100 pi t. The instantaneous potential difference. Vm sine omega t plus pi over 2. V instant. Vm is equal to VE 125.6 radical to sine 100 pi t plus pi over 2. Pi, guys, I forgot to write t here. Write down t, okay? 100 pi t plus pi over 2. This is Vm. Sorry, Vm, okay? This is the expression of instantaneous current across the inductance, and this is instantaneous potential difference across the inductance. Okay? Question 1 in practice 6E, calculate the cell of impedance. What do you mean by cell of impedance? XL. Cell of impedance of coil, cell of induction L is equal to 0.04 Henry. Negligible resistance R0, frequency 100 Hertz. XL is equal to what? Is equal to 2 pi FL. We have frequency and L, just replace into the equation. Okay? Question 3, an AC source of an instantaneous value. This is Vm. Okay? Sine omega. Omega is equal to Vm is equal to what? Question 3. 10 volt. Omega is equal to 50 pi rad per second. Feeds a coil of cell of induction L. L is equal to what? 0.1 Henry. And negligible resistance. Find them. What do you mean by negligible resistance? Resistance 0. Find maximum value of the current Im through the coil and phase difference between the potential. Im is equal to what? Guys, XL is equal to what? Vm over Im. Vm over XL. Do we have XL? No. But we can find it. XL is equal to omega L or 2 pi FL? Omega L. We have expression, omega. 50 pi times 0.1 XL is equal to 15.5 ohm. 15.5 ohm. Vm was given by the equation 10. XL 15.5. Im is equal to what? Im is equal to 0.64. Guys, if the equation is given, the number before sign, if the equation for potential difference becomes Vm, and the number before T time is omega. Because we have only inductance in this circuit, the potential difference, the phase difference between potential difference and the current is 90 or pi over 2 rad. Potential difference leads current by pi over 2. So the last thing on today's topic, a capacitor circuit. Guys, if we have a capacitor circuit with two AC source, okay? We have AC source with the capacitor, a meter connected, series connection with the voltmeter, and connected with the capacitor. This is capacitor, guys, two parallel plates. The capacitor can be used to store electrical energy or electrical field. So the capacitor can be charged only by DC source. Capacitor can be charged by DC source, but we can use capacitor with the AC source as well. Okay? But for charging capacitor, we need DC. Be careful. We will study in electrical oscillation, inshallah, in the other videos. What is capacitor? A device which is used to store or save electrical energy. Capacitor of capacitance, C, is the power of saving, storing charge in the capacitor and measured by Farad. Guys, Q is equal to what? C times V. Charge, capacitor, potential difference. Capacitor is equal to what? Q over V. Okay? So this is very important, these two equations, be careful. In capacitor, when connected to AC source, potential difference lags behind current. This is current, IC. Potential difference lags behind, this is VC, okay? Potential difference lags behind the current, okay? By negative pi over 2, okay? And here by pi over 2 in positive. Did you get? Current leads by pi over 2 positive, but current lags behind potential difference by negative, or potential difference lags behind the current. In capacitor to AC circuit C, we have XC, okay, instead of XL. Potential difference lags behind the current, okay? And it has capacitor impedance. The capacitor impedance is the ratio of the maximum potential difference to the maximum current. Guys, look. So the blue one, current, and the green is potential difference lags current. Guys, look. When current, look, from this point. When current reaches maximum, potential difference, this is potential difference, and this is current. Guys, when the ammeter reaches maximum of the current, voltmeter reaches 0, potential difference 0. Okay? So current leads potential difference by pi over 2, or potential difference lags behind the current by pi over 2. So when the current reaches 0, what happened to the potential difference? Maximum. When current becomes maximum, again, potential difference 0. Okay, so there will be a phase difference between the potential difference in a quarter cycle, potential difference lags behind the current in capacitor to AC circuit. What is the capacitor impedance? The ratio of the maximum value of potential difference, Vm over Im. XC is equal to what? Vm over Im. Okay? And also we can find inductive capacitor impedance by using Ohm's law. VE over IE. VM over IM. V across capacitor, I across capacitor. And also it follows Ohm's law. And also we have two other equations to find XC. 1 over omega C, angular speed times capacitance, and is equal to 1 over 2 pi FC. What does capacitor impedance depend on? Frequency and capacitor of capacitance. The capacitance of capacitor, okay? Frequency, which is inversely proportional, and capacitor of capacitance. Okay? Capacitor impedance measured in what? Ohm. Frequency, hertz. Capacitance, farad. Okay? Cross product. 1 times 1 is equal to what? Ohm, Henry, farad. Which of the following is equal to 1? Ohm, Henry, farad. This is very important. Be careful. If they bring in the Wizari exam, which of the following is equal to 1? They multiply which of the following is equal to 1? Ohm, Henry, farad. Sorry, Ohm, Ohm, Henry, farad. It becomes, sorry, hertz, not Henry. Sorry, this is hertz. Hertz, okay? Okay. In capacitor to AC circuit, potential difference lags behind current. Can we say current lead this potential difference? Why not? Yes. Okay. If you say current lead this potential difference, it's gonna be like this: IC across VC. Is it correct? Yes, of course. Both are correct. In this case, current lead this potential difference. But here, VC and IC, this is the same thing. Potential difference lag, current lead. There is no difference between them, okay? So when the voltmeter reading remains 0, the ammeter reading achieves maximum value. Guys, the capacitor is like this. Imagine you are trying to flowing water into the tank. As the water flows into the tank, the current is maximum, but potential difference is 0, okay? So the potential difference in capacitor is 0 at first, but the current is maximum, okay, until the capacitor becomes charged. So until the water tank is filled with water. When the water is filled with water, the water cannot like flow into the tank anymore, okay? So at this case, the current becomes 0, but potential difference is what? Is maximum, okay? If you open the speaker at the bottom of the tank, what happened to the water? The water again flows. It means that the current again reaches 0, but potential difference becomes 0. So this is current attains maximum, but potential difference becomes 0. So this is the difference between the potential difference and the current. So the phase difference between potential difference and current across the capacitor is 90 or pi over 2. Potential difference lags behind the current. When potential difference maximum, current 0. When current maximum, potential difference is 0. Okay? Capacitive impedance depends on the frequency and inversely proportional, and it follows Ohm's law. It doesn't follow Joule's law. Why? Because there is no power dissipation in the capacitor. In the capacitor, current, power does not dissipate, energy does not lose. Okay? In turn, this electrical energy is converted to the electrical field. The equation of instantaneous potential difference, because potential difference lags behind the current in capacitor, it is equation for potential difference becomes like this: Vm sine omega t minus pi over 2. And instantaneous current across capacitor is equal to what? Im sine omega t. When does this equation is correct? If the question says potential difference lead this current. But if the question says draw the expression or write the expression for instantaneous potential difference and current, when current lead is behind the potential difference, I instant becomes Im sine omega 2 plus pi over 2, and Vm is equal to V instant is equal to Vm sine omega 2. Okay? Both are correct. To find maximum charge or effective charge, use this relation. Maximum charge, use this one. Capacitor can be charged only by what? DC source. How does impedance of the capacitor, XC, impedance of capacitor, XC, measured in ohm, vary with the frequency? Inversely proportional. Inversely proportional. Depend on frequency and it's inversely proportional. Sample problem 6F. A source of frequency 100 over pi hertz. Frequency 100 over pi hertz. An effective potential difference VE 200 volt connected across capacitor 200 microfarad C 200 times 10 power negative 6 farad. Calculate the capacitive impedance. Calculate what? Capacitive impedance. XC is unknown of a capacitor. The effective current of the circuit and the maximum charge accumulated across the capacitor. Calculate capacitive impedance and effective current and maximum charge. QM. Maximum charge can be determined by using this relation. V maximum times capacitor. Okay? How can we determine XC? Because we have frequency and capacitance, we can find XC. XC is equal to what? 1 over 2 pi FC. Replace 1 over 2 pi, frequency 100 over pi, 200 times 10 power negative 6. XC by calculator is equal to 25 ohm. Is equal to what? 25 ohm. The capacitor impedance for this capacitor is equal to 25 ohm. How can we determine IE? Because we don't have IM, use the Ohm's law. XC is not equal to VE over IE. Yes. IE is equal to what? VE over XC. Do we have IE? Yes, 200. XC we didn't have, but we found 25. I effective is equal to 8 ampere. Maximum charge accumulated in the capacitor is equal to what? Charge is equal to CV. Maximum charge, C maximum volt. Do we have maximum volt? No. Vm, we have VE is equal to VE times radical 2. Capacitance of capacitor 200 times 10 power negative 6 times what? Times 200 radical 2. 200 radical 2 times 200 times 10 power negative 6. The maximum charge is equal to 5.65 times 10 power negative 2 coulomb. Okay? Practice 6F. Calculate the capacitive impedance of capacitor XC. What is unknown? XC. The capacitance C 2 micro, convert micro to farad. 2 times 10 power negative 6 farad. Across the source, this is frequency. 1 over 2 pi FC. Replace. 796 ohm. This is the capacitive impedance. A source of instantaneous potential difference. This is the equation, guys. The number before sign for potential difference is Vm. 10 volt. Omega. The number before T, 100 pi. Rad per second. Connected across the capacitor of capacitance C, 1 microfarad, which is equal to 1 times 10 power negative 6 farad. Calculate the maximum value of the current. What is unknown? Im. And phase difference. Phase difference is equal to pi over 2. And potential difference leads the current. Okay? A lag is behind the current. Pi over 2. Or negative 90 degree. How can we determine Im? Im, guys, look. XC Vm over Im. Im Vm over XC. Do we have Vm? Yes. Do we have XC? No. How can we determine XC? 1 over omega C, not 2 pi FC, because we have omega. Omega 100 pi C 1 times 10 power negative C. XC is equal to what? By calculator, XC 3184.7 ohm. Replace into this equation. VM 10. XC we didn't have, but we found. IM is equal to what? 0.00314 ampere. Phase difference, because we have a capacitance in the circuit to AC circuit. Potential difference lags behind current. Okay? And it should be negative. Potential difference lags behind the current by pi over 2. Guys, this is wrong. Delete this to equations, okay? Not important. Okay, we finished this today's lesson. That's all. I hope you get benefit from my lesson. Keep up your best doing. Inshallah, in the next lesson, I will be uploading all lessons in the section 3 in the chapter 6. Inshallah. Thank you for listening. Goodbye.